Yeah, hi everyone. My name's Johannes. We heard the title, so let's take a little look at address sanitizers. Let's set the stage. First of all, this is kind of a work in progress report. This is not finished. This is not cleaned up. So the numbers that we report are a little like hand wavy. They give you ballparks and they give you ideas, but don't pin me down on things. And there's a lot of room for improvement. Thanks to Aaron and Rahul who helped me collect some of those numbers. So kudos to them. Let's start. So in my day job, I work with simulations or with people that have simulations, and they modify their simulations to run things. They build them, they run them to get maximum science output, and then these things start generating maximum science, and then they crash. And that's pretty much, this is the situation I see in front of me quite often, and that's kind of the end of the road. And then you're like, oh, damn. And then you start, debugging, but debugging is hard. And one thing, for a lot of these errors, what you would like to have is a sanitizer, right? Because that kind of helps you narrow down what's going on, where is this coming from? So sanitizers, especially the address sanitizer, helps you track down bugs out of bounce bugs and stale pointers. It does so by an instrumentation pass and a runtime. It uses shadow memory and red zones, and we get to that, and it has been a staple in LLVM for a long time. The other thing that I kind of focus on are GPUs, because where we are, we care a lot about GPUs and the performance they give us. Obviously a powerhouse for modern HPC. I heard you can do AI with those things as well. And for now, I'm assuming dedicated memory. That is not strict assumptions, but that is kind of the harder case, so let's go with that. So in a nutshell, what is happening? We have code in an architecture, and if you write correct code on the CPU or the GPU, you're happy and life is great. So not a problem whatsoever. The problem is when you write buggy code. On the CPU, you write buggy code, you're unhappy because it crashes, you use the address sanitizer, it tells you where the problem is, you fix it, you're happy. So what do we do on the GPU side? I mean, yeah, as mentioned before, we should just use the ASAN, right? And that's what people did. People quite literally ported the ASAN onto GPUs. I mean, it seems like a great idea. So there is a complication with that idea, though. So what happens is, if you compile your code and run it, you get fast CPU code with like a good compiler. And if you then run it, port it to the GPU, and you run it there, you get faster code. That's the whole point of doing that on these massively parallel machines, right? So you improve, you get faster results, you can run bigger things. The problem is if you compile and sanitize your code and then run it, on the CPU, your code takes a hit. It's slower than it was before. But it turns out on the GPU, it's much slower. And that's actually a problem. Because if your problem only occurs for big runs and so on and so forth, or if you need a lot of memory, you cannot add a lot of overhead, either in memory or runtime, or it just becomes completely unpractical. There's also the compile time angle, but let's not focus on that too much. Okay, so I can tell you it's very slow, but I actually have some data to back it up, right? So we looked at XSBench, which is a little proxy application for nuclear reactor science, I think. They do things that are important. We have like 5.5 gigabytes of data that is moved to the GPU, so that's like a non-trivial amount. And it's a proxy application for the full OpenMC Monte Carlo nuclear reactor simulation code. We'll see that in a second again. The fun thing about it, it comes with CUDA versions, OpenMP offloading, HIP versions, and others, and it's like really easy to build. So it's a great way to do some testing. First thing we did is we took like a V100 system with the OpenMP offloading version and the CUDA version, and we used the NVIDIA Compute Sanitizer tool, which is not instrumentation based. It runs on an executable after the fact. It does more than address sanitizer. So that as a word of caution. Default run times 2 seconds and 0.4, and then with this compute sanitizer, we get like slowdowns of like 25 to like 130x. That's bad. On a more modern architecture, an A100, that is one order of magnitude less, which is better. So we're looking at 4 to 40 x slowdown. Again, this does more than address sanitizer does. So let's look at the address sanitizer that AMD ported onto their architecture, onto their GPUs. Again, the OpenMP offload version and the HIP version, and we get a slowdown of basically 10, 11x. That's kind of our ballpark here. And if we look at our results, we're looking at a slowdown of like 2. So that's an improvement of 5, and in addition to that, we don't have the memory overhead. And I believe there is more possible, but let's get to that later. So this is just this little proxy app, one kernel, you get like a single data point that tells you something, but maybe not all of it. So I run the full OpenMC application, and I looked at the kernel times across all of them. So blue is the base. Red is we sanitize everything but shared memory, like the fast _ shared stuff. And yellow is we sanitize everything. And what we see here is that all the kernels have like the overhead hovers around 2 across the board, which is good. It also tells us that, we also get some other like results. If we sanitize everything in that run, we had like a 2.3x slowdown, end-to-end, what the science produced. If we remove if we don't sanitize shares variables, we get a little bit back. If we only do heap and global variables, like your CUDA malloc style thing, you only get 80% overhead. If the instrumentation alone, the way we do it right now, and again, this can be optimized, costs us 30% of those 80%, just saying. And if we added some optimizations. You can ask me, I have backup slides for those. That actually got us back from 2.3 to 1.7% on end-to-end overhead. So these are the ballparks we're talking. So now let's take a look why this is. First, how does ASAN work? Let's assume this is our memory, right? You have a double array in the top, and you have a single long at the bottom, and you have stuff in between I don't care about. Now, what it does is every time it does an allocation, it puts fixed-sized red zones in front and before and after, and every allocation. And then it has a shadow memory, which basically has the same layout as the original memory, but on a scale 1 to 8. So somewhere with an offset or a specific location, there is this shadow memory, which just mimics the real memory with a 1 to 8 mapping. And then if you have an access, let's say A of I, what happens is if you access inside of the array A, everything is fine, and that's kind of what will be reported. If you access kind of the red zone, what happens is you get an error, which is great, because at least you know you did something wrong. The problem is if you happen to access inside of another array, another variable, or just in the middle of nowhere there is no red zone, you probably will get away with that access without it being reported. So that's also kind of a little iffy. So how does this work? Basically, before it does instrumentation, before the access, you do a check if that address is valid. What it does, it goes back to the shadow memory, it loads the value in the shadow memory, and basically the values there tell you if the memory is okay, to be accessed. So the green one obviously kind of works through. In the yellow case, it comes back because it loads values out of that shadow memory that indicate red zone. It reports an out-of-bounds error, and it can do certain things here. And if you happen to hit another non-red zone in the shared memory, your program just continues running. So that's kind of unfortunate. Now, let's recap. CPUs and GPUs are different. That's kind of my main point on all of this. The environment in which you do things is completely different. One is very closed, the other one is very open. You have a lot of memory on the CPU and not so much memory on the GPU. And you have different kinds of memories on the GPU that you explicitly program and you really care about. While on the CPU, people don't really explicitly program their different memories. ASAN has a fixed overhead. It basically introduces a second access for each one that is in your program, more or less. It has at least 12% memory overhead. If you have a lot of small allocations, it's more. And it can have false negatives. And then if we actually run the numbers and run these things, we see an order or two of magnitude in terms of decreased performance. Also, my main problem, honestly, was not the 10x slowdown or the memory overhead. My main problem was that I don't have a version in open, an upstream version of an ASAN that I can use on a GPU. That was my main issue. Anyhow, let's take a look at what we did. First, think of, there's our memory again, as before. Think of a pointer. What does a pointer actually do? A pointer kind of has some bits that kind of technically represent what object you're pointing into. and some bits that give you the offset into that object. I mean, this is simplified, but if you think about it, this is kind of what a pointer does, right? So, and now the idea was, why do we, I mean, let's introduce a level of indirection, because that always solves problems in computer science. So I introduced kind of my own little MMU in software. Every time I do an allocation, I put an entry in there. I say, this is the base pointer of the allocation, and this is the size. Every time I deallocate, I basically put the size to -1 or whatever, and then I know that allocation isn't valid anymore, right? Here we go. How does our pointer now look? Our pointer now points into that MMU unit and says, I'm entry 15. And then the offset, and then through that MMU unit, you can find the object where it's supposed to be pointing to, and the offset just stays the way it is, because you want to allow people to do pointer arithmetic, you want to allow people to do get element pointers, and so on and so forth, which they can, because the offset is exactly where it's supposed to be. So they can just add 5. That's okay, it's all cool. Now, if you have a little piece of code, let's say a loop that increments an array, each element in an array, what happens is first we do a lookup. So think about it, A is this pointer here, so it has an object ID and an offset. Inside of that allocation record, we can basically find the base pointer and the size, which means that we now have a base pointer, size, and offset before the loop. We only have to do that lookup when the base pointer is defined, which is generally, often, not always, often, at a place that is much better than where the axis is. And then inside where the axis is, we do an actual check. Again, you could hoist this, but let's not. Let's say we do the check where the axis is. And what you check here is offset plus I smaller than 0, and is offset plus I smaller than size. That's it. There's no memory access next to your real axis. That's kind of cool. Obviously, you have to actually rewrite all your axes, because now you fiddled with the pointer, so A is not a real pointer anymore, so you have to kind of deal with that. But that's doable. Now, offset is where it is, but what would happen if somebody overruns their pointer, their offset? You would basically have a broken object ID, and then your ASAN instrumentation would crash. That's not great. So we introduced some magic here to make sure, if somebody overruns their offset, we can detect that. So again, on device, every time we do an allocation, we put it into our record. Getting something from the record is 16 bytes loads in a lookup. We'd only need bit comparisons and bit operations and comparisons for each access to do the check. And all of this is great for 64-bit heap pointers, for which there's a few allocations. But if you're on a device and you have shared memory and stack memory, for which there are a lot of allocations, think each stack allocation exists per thread, so 10,000 times your number of stack allocation. And those are 32-bit pointers, which is also kind of semi of a problem. So that scheme is actually not as great. We did it initially, and it works, but it's not as great for stack pointers. So what do we do instead? First of all, we introduce an address space, like what kind of pointer, where does it point to, into our fake pointer. And it always has to be at the same location, because if you get a pointer and you don't know their origin, you need to check that first to kind of guesstimate what this pointer is. And then, again, this whole thing is 64-bit, right? That's our pointer size. What if we have a 32-bit pointer? Like, if we start with a 32-bit pointer, we first, in our 64-bit thing, we still put the address space in the very beginning, and we put the magic and offset at the very end. Again, this is embedded in a 64-bit. But then we take the size of the object and embed it inside of the pointer. Because we started out with a 32-bit pointer inside, and we embed it into a 64-bit pointer. We put the size in there, and then we put the real pointer in there. So now our entire metadata lives inside the pointer that we pass around, and there's nothing stored anywhere. It comes with the pointer. Okay. Now for each heap, now we do the allocation, the registration only for heap allocations. 32-bit pointers are replaced with 64-bit pointers everywhere. Remember, this breaks down if somebody would store away a 32-bit pointer as a 32-bit pointer. But it turns out nobody actually does that, because it's actually hard to do. It's not impossible, but it's kind of hard to do, so people don't do it. There's no good reason to do it anyway. So we could detect it, or we can detect it, so it's not that bad. Address space check, and then the 16-byte load, potentially, depending on what kind of pointer it is. For the lookup, the check is the same as it was before. And for 32-bit pointers, like shared memory and stack memory, we have no memory overhead. Okay, now I have some numbers here on what our current values are. You could switch them around, and you have more bits inside of the pointers that you could reuse if you really needed to. So this is more of a one configuration among many. Okay, so a few more things. So the lookup now actually has to return the address space, and the check has to know the address space because everything is address space dependent because the pointers look different. And if we already know statically that a pointer has an address space, we don't have to do this. We can even verify that the user gave us the right address space and so on. Okay. How do you register these heap pointers? I mean, effectively, you just overload the mallocs and the CUDA mallocs of this world and just say, okay, do the actual thing, and then register it in my MMU table. It's that simple. There's no magic going on. Okay, how does this look if you get an out-of-bounds access? Because these are nice pictures. So you get, it says, okay, an access, a read, a write. I mean, nowadays it says read or write of a certain size. Technically, we can have the PC here. The block and thread ID are actually what thread caused the issue. Then you get a device-side stack trace from the GPU, which is completely software managed as part of this. Because I wanted stack traces, and I don't know Dwarf, so I made my own. It's not a good idea, but it makes nice pictures. So you get this software-managed device-side stack trace. Then you get information about the allocation. You get where is it, what was the name, what was the backtrace of the allocation. So you get all of that thing about where it came from, which is pretty cool to, if the pointer you load is from somewhere and you don't actually know where it came from, and now you can pinpoint where that came from. And at the very end, similar to the AddressSanitizer that shows you the shadow memory state, I'll show you the pointer state for no particular reason. Okay, we can do this with shared memory, not only global memory, but shared, and there's a twist to the whole thing. I talked about GPUs a lot. I talked about 32-bit shared memory pointers and so on and so forth. But as part of my abstract already, and given the fact that I put offload in parentheses, you might have noticed nothing of this scheme is dependent on the GPU. I kind of used it there and I needed it there, but I didn't actually have, there was nothing about it that was GPU specific. So let's get rid of that. Let's just say ASAN via software managed virtual memory, right? And in the abstract, I promised I'm giving some numbers. So yesterday morning, I did some experiments, so I have some numbers. I took a naive matrix multiply, 1024 to the power of 3, the input sizes of the matrices. And I ran it on an AMD EPYC processor because I just had that lying around. And what happened? So I ran this version, a hacky, port this from my GPU implementation to the host and just basically rip it out and just stitch it together, versus the baseline and ASAN, like a regular Clang ASAN. And what you get is this, my hacky stitched together solution was 6% faster on that example. Okay, that's kind of in the right ballpark, right? That's not bad. But the fun part was it had, effectively 0% memory overhead, 0.0001 of the pages that actually were touched compared to the 30% of ASAN. And I thought that was kind of cute. So that was cool. And I believe there is, again, lots of things that we can do, and I believe there is lots of room for improvement. We have done 2 or 3 little optimizations. Some others are currently being worked on, including hoisting things and so on and so forth. But the point is, we already got rid of the memory, which was a clutch in the original design always. And now if we can get rid of a few more of those accesses and checks out of hot loops, we probably get our overhead in both dimensions down to a level that is really nice. Okay, let's summarize this. We report various kind of errors, including if you allocate something that is too large for us to handle because we have a natural limit. Depending on your configuration of pointers, you can only handle this. You could fiddle with the bits, but there is a limit to it. We can tell you if you have a bad pointer. So if you overwrite, effectively if you break the magic bits or some other things, we will just tell you that's a bad pointer. You did something with this thing or pulled it out of thin air, I don't know, but it's not good. Out of bounds, negative and positive offset bigger than the size, cool, yes. We can do heap after free for everything that is in our MMU because we can update the size after the fact. So if we put the stack things in there, we could do it. Heap, we can do it. I have ideas on how to do use after free for the 32-bit embedded pointer things. I believe that is doable, but we can discuss that later, and I'm not sure how useful that is. And we can tell you if your code assumed the wrong address space. So basically your code had static annotations of a certain address space and you ended up with a different one because we kind of track it anyway. Okay. We have very little memory on the GPU, so we should avoid memory overhead. We are generally memory bound, so we should avoid additional accesses, especially in loops. And we have different memories, so we should have something for fast memory that works for fast memory, something for stack memory that's good for stack memory, and only for the heap, slow heap memory, we can do actually overheads, not for everything else. Okay, I'm out of time. Thank you.
Any questions?
Okay. Does it matter, like as a developer, I can actually inspect the value of a pointer, right? For, if it's the hash key or something.
Yep.
But actually, if I write like something like a JIT, I can look at it and do
Yep.
tricks with it, right? Like,
Yep.
It's not immediately obvious how this handles. So.
Okay, so there's two things. One, people could just fiddle with the pointer. They do an pointer to int, and then they start, doing all sorts of things with that thing, which is generally fine. If we call an external function, let's say we call it printf, right? And we pass one of our pointer gets passed. What do? We automatically put an unpack call in there, which is effectively a lookup, but without the check. And then we pass the real pointer out. And you can also ask the system to get the real pointer for a fake pointer. So we do this to do external function calls, like printf or something else. And you could do it manually if you like, but yeah. So there is a chance we break things if people do that, especially if they do an into pointer. We could look up there too. I mean, actually, we could do the auto unpack everywhere if we wanted to. The problem is you can't pack it back in. Once it's kind of out of the bag, it's kind of out of the bag.
Very interesting work. Thank you for presenting this. I want to point out that this feels kind of reminds me of Intel MPX. Intel MPX.
Okay.
It's a deprecated extension. They also had this kind of a table of bounds in memory. Mm-hmm. My question is, how do you manage the lifetime of the entries in your bounds table? Like, say you deallocate memory, not all of your pointers are gone yet. So
yep.
Some kind of quarantine? Or?
So as of right now, so there's two things. My MMU, my little table, just exists for now. I give it a fixed size. You can make it grow and you can make it a linked list or whatever. So it has a fixed size for now. And I never remove entries. What I do is if you deallocate a pointer, I update the size. And then I basically put the size onto invalid. And then when you access it later and we do the lookup, we can be like, hey, this is a user after free because you just accessed something that has been deallocated already. And then what happens if I run out of space in my big thing? I mean, if that is a problem, we have to come up with ways to basically allocate new tables and link them together. But I would never get rid of things, really. You can, when we had the stack stuff, we actually added tags into the pointer and the allocation table such that you can reuse these places, which you could do. I mean, you can use a couple of bits to reuse the place and reuse the pointer, and you then still know, even if you point to location 17 into your table, you can compare the tag of that thing in your pointer, and you still know if you actually meant this object or the object that was there a while ago. So it kind of, that way you can reuse these entries, but so far it's just no need.
Thank you.
So, since you're looking at out-of-bounds access and all this stuff, it looks like UBSAM can cover that. You look at the UBSAM as lighter and less memory overhead.
I have not compared it to UBSAN. I was not aware that UBSAN does bounce checks.
I think so.
And I mean, if it does bounce checks, I also don't know how it does it. But yeah, I have not compared it to UBSAN.
Any more questions? Okay, let's thank Johannes again.